Hi guys, welcome back to the System Design interview sessions with me. Today we're going to talk about Google Maglev. Before we start, I just want to make a recommendation to how to better prepare your upcoming system design interviews, or you just simply want to improve your system design skills uh, for your work or for a school project or just for like a hobby. It is really valuable and helpful if you can read articles, white papers, blogs from the top tech companies like Amazon, Facebook, Google about like how they design services, component, or any tools. It will open your mind about especially going through all those design principles and implementation details. It will definitely help you if you want to adopt any of the concept or design principles to the upcoming interviews or for your company project. And today we're going to talk about the Maglev. It is one of the popular like white papers provided by Google, others including like the big table, which is the inspired quite a few designs of different popular databases and the Google file system, how they manage the chunks at different servers, coordinators. It is always inspiring. And for Maglev, it is a load balancer designed, developed, and adopted by Google to handle their planet scale traffic volume. Um, in a nutshell, it is a software load balancer working at layer 3 of the OSI model, which is network layer. If you're not familiar with OSI model, please go take a look. There are many resources to explain what is the OSI model and what different layers does, from the physical layer, bit link, network, all the way up to presentation and application layer. You can have like more detailed learning to find some materials. And for this session, I'll just skip that. But if you want, you can leave a comment. I can share in the follow-up videos, or we can have one-on-one sessions. So before we get into how Google Maglev works at a high level and in details, I just want to make sure everyone is clear about how internet is connected. It will be super helpful to understand some of the design concept for Maglev. So in general, like you can imagine, uh, the whole internet is connected by different networks. Your local network provided by different ISPs and how they connected together each city, each country to form the global internet. And for that, of course, we need IP address to find like where the traffic is initiated and where it is destinated to. So that's a concept of like routers, which manages all the, as you can see from the name, all the routing um, functionalities, where it is come from, where it should be redirected to, and also it's not only one or two or routers. There's so many routers on the internet connected by border gateway protocols (BGP). If you want to take a look, take a note. You need to some of the details that be helpful, and then that's how the internet is connected. And also there's a concept of like domain names, because especially for browser or website, we don't remember the IP address. We only remember the domain name. That's google.com, facebook.com. And then, as you can imagine, we need some mechanism to map the domain name with the actual IP address. And also for some domain names, it has like multiple IP address. For example, Google. If you tap your local browser, it will be redirected to the nearest front end or point of presence provided by Google to reduce the latency and provide the best um, customer experience. And so there are multiple layer DNS resolver, which is just to do what I just described, like to map the domain name to IP address where it will redirect your um, request from your browser or your mobile app where it redirect to. And also there's different levels, like your local level, maybe your local area network, or like your company, your school. And then there's upper upstream DNS resolver, maybe at your regional or city level, and so on and so forth. Normally, I think it's like 5 or 6 levels before you can reach the root DNS server. Root DNS server, as the name suggested, it contains all the information on the internet about the DNS names, where their IPs will be stored. There are only 13 of them distributed globally. It is managed by ICANN, and it stores reference to top-level domain name servers because, as you can see, only 13 of them cannot store everything, and it will not be efficient if, like, even though to store everything and like to handle the millions or billions of requests every day for domain name resolving. So it stores reference to top-level domain name servers like .com, .net, .ie, .nl, etc. And top-level domain DNS servers, then they are distributed globally. This stores records for top-level domains and has a limited number. It has a reference to authoritative DNS servers. Authoritative DNS servers is the actual server that stores the exactly domain name to the IP address mapping. There are public ones like GoDaddy, where you can host a company or your own website with a domain name, or it can be dedicated domain name servers like Google, Facebook, Amazon. They have their own authoritative DNS servers to manage their large group or network. So it is not necessary for everyone to have their own. You can use like public ones, but for if you are managing a tremendous amount of like a network endpoint, it is good and efficient to have your own. So you have like more flexibility to fine tune those and customize. And normally how DNS resolver works is, for example, you type google.com in your browser and you don't have like a local copy. Hey, what is that address bounded for that? There's different levels of caching. Your browser can cache like Chrome and Firefox provide, and your own PC has a copy on the computer level. If none of this found, it will send out a request to your local DNS resolver. Hey, what is google.com address? If it doesn't have, it will contact upstream. It's iterative approach. If any of the upstream DNS resolvers have the cache or copy of that, it will reply or respond to your request to your local resolver, and your local resolver will respond to your browser. And also during the process, everyone save a copy or caching the request. It has the time to live, and then when it is part, the process is repeated. And so any of the upstream DNS resolver can have the information and will reply back through the same route back to your local browser. And if not, the top layer DNS resolver will contact the DNS server, root DNS server, say, hey, what is the reference for, like, for example, .com, top-level DNS servers? DNS server, root DNS server will reply the reference to the top-level DNS server. And then, so this resolver will contact the top-level domain DNS server. Hey, where is the google.com stores? And then top-level DNS server has a reference to all the authoritative DNS servers for that specific domain, like .com. And then it will send the correct address, like s1.google.com as the authoritative server. And then the DNS resolver will contact s1.google.com. Hey, what is current address, IP address for google.com? And it will respond with the IP or list of IP. And this resolver will patch that before send it back to the lower level DNS resolver. And then this guy will cache locally as well and reply to the requester for that. So this is how does it work, how the global internet is connected. And also you may ask initially, where do I get my IP? How do I know what's the gateway, where's the DNS resolver? So when your PC connected to a network through a router, either at home or at company at school, it will send a request called DHCP, Dynamic Host Configuration Protocol. It's like a broadcast request to the router or the local area network. And whoever is responsible for that, normally the gateway, it will receive the request and it will send back the response for the IP address for the device, which normally have a NIC network interface card, so that will be banded. And also it shares, hey, what is the gateway IP? So next time the request will be sent through the gateway instead of like a broadcast message or the multicast message. And then, of course, the DNS resolvers IPs, it belongs to the internet service provider, would be the broker like Vodafone or your local network service providers, and also like underlying would be provided by the global ISPs. There's only a few of them. That's pretty much the fundamental knowledge about network. And then let's talk about high-level Google Maglev works. So let's imagine the as a local network, we have different client, maybe like the company level. All the requests go through the exchanger that manages the local network. If you're not connect different local network together, like exchanger would be enough for all these clients to communicate among themselves. But if you want to go out, like router is required. Of course, there can be multiple exchangers connected to one router. And then, yeah, the router will do the BGP border gateway announcement to the public network. Hey, these are the list of IPs I'm managing. If you see the destination for these IPs, please redirect to me. That's basically what BGP announcements does. Of course, periodically it will update to make sure like the date still is fresh and it's still the case I'm managing all these IPs. And so in the case of Maglev, the request from, let's say, from this client, we'll go through the local router, public network router, and there's multiple hops around different networks. And then here, it will redirect to the Google front-end up. The router will receive that packet. And then from here, there's protocol called equal cost multiple path protocol for network packet management, and will send or distribute the packet evenly among the Maglev instances. And so how they decide which one to direct to, that's from one step back is the Maglev instance themselves will announce the VIPs they are managing or they are handling through the same border gateway protocol. It's a protocol well recognized across the internet by routers, by exchangers, by network card. And so each Maglev will make announcement to the Google's router, hey, this is the virtual IP or list of virtual IP I'm managing. And the Google's router will announce to the public network, the same as your local router announced to the public network, hey, these are the IPs. For the router, like virtual IP concept is created by us. The router doesn't distinguish about which IP is virtual, which is physical. They just makes announcement through the internet protocol. Hey, these are the IPs I'm managing. If you see them, redirect to me. And so, yeah, that's why the router knows like where to distribute or forward the packet to. And then when the router receives that, it knows which Maglev instance it's handling those, and it will use the ECIP protocol to distribute the request evenly to different Maglev instances. And then when the Maglev instance received that, it will see, hey, which virtual IP it is, and then it will find one of the backend service endpoint through consistent hashing, and then add a wrapper through GRE, generic routing encapsulation, on top of the existing IP headers, so it knows where to forward the packet to the backend service selected. Of course, we'll go into the details of Maglev instance, what it does, what is included. Let's just focus on the high-level flow, how it works. And then the backend service, they can handle the request directly, or it can have like nested layers and redirect to another backend service belongs to another backend pool. So as you can imagine, for any Google service, it is impossible to have just one instance or one service to handle the request. It is always a cluster or pool of service to handle the request for scalability, for reliability, those type of things. And then eventually the backend service will receive the packet, and then it will uh, remove that layer because like you can see in example later on, it says on the header, it says, hey, this is a GRE wrapper. I'm just a wrapper. Please remove me. And so because it's a defined protocol, the network card uh, can know what to do with those. And then after the processing logic or um, for data storage retrieval, the backend service will send the response directly back to the router. It will bypass the Maglev instance. That is just how it works. It will save the one, it remove one less hop. So these are through a specific mechanism. So we can cover that a little bit in later if we have some time. Um, So that's literally how Maglev works at this level. The request will go through the internet work router and until it reaches Google front end, the router handles the virtual IP of the IP is designated for, and the router will distribute the packet request evenly among the Maglev instances who announced that virtual IP they are handling. And Maglev will add we'll find the backend server, we'll add the IP header on top of the original request, and then forward the packet to the backend service. Backend service will do the processing and then send the response back directly to the router. And of course, with the destination address. Um, and the router knows where to redirect them back all the way back to the client who made the request. So that's the high level how it works. Now, to talk about Google Maglev, it is a big topic, and if I'm speaking at too high a level, and if you have like any detailed questions, please leave a comment. We can go through them together. And also, Maglev is really generic and broad topic. It is nearly impossible to get everything in details in a 30 or 45 minute session. So please, if you want to learn more, please read the white paper. And if you have any questions, schedule a direct meeting with me or leave the comment. We can figure things out together because not everything or the implementation details are included in the white paper. And we might need to have proper discussion to make some assumptions about how it is exactly implemented. During the process, we can list a few different options. We can discuss the trade-off, the merit, advantage, or disadvantage of different solutions. I think that's the important thing. How it is actually implemented, of course, only the Google engineers, some of the Google engineers who work on this project, which know all the details. And so like start from the request here we covered from the router, we have the packet with the virtual IP. It will be routed through one instance of the Maglev server through equal cost multiple path protocol. If you want to learn more about that, please take a look. So it's just a network protocol. As the name suggested, it will redirect the or distribute the packet evenly across a few peer servers um, at an equal cost. And the network interface card receives the incoming packet. It will store it in the packet pool here, this one. The packet pool is pre-allocated at the instance startup time. It is just a memory buffer memory shared between NIC and the folder process. So folder process is one of the important component or process for the Maglev server. It will do all the taking all the incoming packet, do the processing, and send it out through the same network interface card. So it is one of the key component for that. Another key component including the controller process. So it is responsible to announce the virtual IP to the router through BGP, say, hey, these are list of virtual IPs I'm responsible for, or it can withdraw different a certain IP or list of VIP from the router. Hey, I'm not responsible or I'm not listening to this list of virtual IPs anymore because of health issues or because of different issues or just the configuration changes. Or it can withdraw or denounce completely from the router. Hey, I'm no longer working for different reasons. So it is responsible for communicate with the router and about the hey situations, what I can handle, what I cannot handle. It is also responsible for check the health of the forwarder process, which is the essential process for Maglev server. So it is important. We know for sure like the forwarder process is working well, it's not working well. So we can see talk, communicate with the router on the admin dashboard to increase the load for us or reduce the load or completely remove the node from the cluster, Maglev cluster. And also it is responsible to update the config files about what virtual IP is responsible for, the virtual IP mapping to the backend servers, which backend pools are connected, and how many servers and their endpoint in the backend pool. So it is one like an interface to all the point of contact with the external work, like in the control plane. And also the configuration changes can be pushed from the admin portal as for the generic or common ones or less frequently changed one. For immediate or ad hoc configuration changes, there's other mechanisms like PubSub. So the controller process subscribe to a topic or event for and basically listening to the changes for configuration changes. And of course, on the let's focus on the forwarder process because it is the most complicated one in the Maglev instance. It has, for example, it has a configuration management module to pull the configuration, pull information or metadata from the configuration files, like the virtual IPs, virtual IP to backend pool mapping, like backend pool to backend service endpoint mapping. So that is special module works for that. And also, yeah, maybe let's go through some of the simple ones first. There's health check module to monitor the health of the service endpoint as well. So it will connect directly to the backend service through their IP and the port number and send periodically ping messages. That's the typical health check mechanism to see if this backend service are still alive or working functionally, what is the latency, this type of information, and then they can decide do they need to remove it from the list of them IP or like it continue as zero. And of course, the health confirmation module, it is response to the controller process. Are you still working on also other information about the latency, how has the workload, like CPU usage, etc. It will be received from here. And then back to the forward process. Where we set the packet arrived at the NIC level. The NIC will store the request in the packet pool, which is shared between the NIC and the forwarder process. This is to improve the performance or reduce the latency or reduce the overhead, potential overhead cost to between the Linux kernel and user space. So this is completely bypass the kernel space, and also there's no copy of date, in this case, the packet whatsoever. And all the process we use like pointers to the packet pool about to refer to or point to the packet stored in this packet pool. So the packet will store once and won't be copied anywhere. So that's the one important design concept for Maglev, and use the shared memory space between NIC and the forwarder process. It saves only once, and for the rest of the process, we only use a pointer or reference to the packet location in the packet pool. So as you can imagine, it improves performance by removing the necessity to uh, use the Linux kernel or copy the data. So there's another thing after store the packet in the packet pool. That's a second type for the NIC. It adds the new pointer to the packet, as we said. Like we only manipulate with the pointers once the data is stored. It adds the pointer to the ring queue, which is to manage the incoming packets. So you can imagine it is the queue who is responsible for the incoming packets. It is received or like processed, and then after process, it will be and the space will be freed and become the reserved queue. And so from here, you need to know like the pointer is saved in this queue by the NIC, and the pointer to make sure like, hey, this is a new package coming. And this queue is used to manage the incoming packet. And then for the queue itself, it is a ring queue. It's not a traditional queue, which means it is in a circle, like a ring. And then important concept that the three pointers are used to manage or manipulate the queue and take all the operational tasks. So for example, there's a received pointer that can be moved along. So for example, a new packet arrived. The NIC will save it here on the in one of the reserved space. So the reserved pointer is moving forward, and then the received pointer will be moving here. That means the current location of the received packet. As you can imagine, could be millions or even more than that. And in theory, it moves really fast. And then the process pointer. Once the process pointer, the forwarder process will hash the file tuples of the incoming packet, original like in the received position, and then it will send to a different queue. So that's a dedicated module called steering module. What it does is it will hash the file tuples of the incoming packet, which is listed from the queue queue position. Once it hashes the file tuples, it will distribute it to different receiving queues for further process. So this step here, the steering module, will take the reference and find the packet, calculate the file cache of file tuples, and based on the hashing result, it will put into different receiving queues to be further processed. And then it will advance the processed pointer to the next one. So the received after processing, it will be the processed one. So it will be moving to the next one. And also the received will be moving as well, reserved will be moving. The three pointers are chasing each other. So that's where you think like all the coding interview questions finally making sense because it is actually used in some of the cases. And later on, we'll go through this another ring queue, the same structure, but used for the outgoing packets. So this one is managing the incoming packets. Like I said, the stream module will distribute the packets to different queues based on the hash values. And here are some details. It's highlighted in the white paper as well. In this case, let's imagine like the two CPU cores, two CPUs, and one CPU is with 8 cores. So 7 of them are dedicated to packet strand, which we can see here. This packet strand is responsible for the actual manipulation of the packet, adding the IP header, adding the GRE header to make sure like the backend service knows like they hey from that the wrapper outside the actual or the original IP is included in the packet itself. And so as the paper listed, only one car is dedicated to steering and mixing maxing module. The rest is dedicated to the packet thread. So each packet thread is attached to one receiving queue. So they can take the packet reference from the queue and of course locate them from the packet pool and do their take the operations. And after the processing, it will put the pointer or reference to the transmission queue. After the processing to mark it, hey, these packets are ready to be sent out to the backend service. And as you can imagine, several of the cores are dedicated to thread, packet thread. It means there's complexities and a lot of responsibilities for this packet thread. So let's go through them one by one. So the first step, the packet thread will recalculate the file tuples of the packets. So this will reduce the necessity of all the overhead or thread switching from the steering module to the thread packet, because the hashing can be calculated really fast in nanosecond. If we want to do like a thread switching or computing time, like recycle, it will take longer. So this makes sense. We just rehash for the simplicity and the fast performance. And then after rehashing, it will check if the hashing if that record in the connection tracking table already. So the concept of connection tracking table is for any incoming request, if we see it at first time, and like say in this case, it will check. If it's not, it will do the file tuple hashing and find the destination for the IP and the port in the backend. This is physical IP and the port to one of the backend service in the backend pool. And we'll save the copy here. So next will be the follow-up segment or packet route with the same source and destination. It will look up through this lookup table. It's in memory, it's super fast, so we don't need to match the request to, we'll skip the process match the request to backend service. It will look up the file tuple hashing here and find the IP and mark it as done to put it in the queue. So it will save all the lookups. So the connection tracking table just stores the important thing is the key, if it's the file tuple hashing value, and also destination IP and port. And maybe other information, maybe the server ID, something like that, session state, expiry time, all the metadata information, which is not listed in the white paper, but we can imagine we can store some other information to help making the decisions. And I would imagine that definitely would be a time to live field here, so those information won't be stored forever. And so if file tuple hashing already exists, that's easy. Find the IP, add the wrapper, add the IP header, add the GRE header, and put it in the transmission queue, ready to be processed by the maxing module. We'll go to there later on. And if it doesn't exist, then we need to check the virtual IP lookup table to see okay, that's one step. We also need to check if the virtual IP is like a double check or confirmation. If the virtual IP is actually managed by this Maglev instance. If not, it simply drop the packet. And if so, it will know like which lookup table to looking for, because for each virtual IP, there's one dedicated lookup table. For example, this might be like for the search service. The other one would be for like Gmail service. So the lookup table, let's see if we need to go into the details now, maybe later. Like lookup table is populated by a Maglev consistent hashing mechanism, which is slightly different from other consistent hashing Maglev. We can go into the details later, but as you can see, it's just lookup table. It has the IDs, which is the hash value, and also the backend server IP with port number. Also, it could have like other metadata information if necessary, which is this part of information is not included in the white paper, but we can, of course, we can decide if it makes sense to have other information listed here or not. And so the packet thread will find if the virtual IP exists, and also if so, which lookup table to refer to, and then with the hashed file tuple value, it will find the which backend server it will send or send the packet to by adding the extra IP header and also the GRE packet. I think the GRE header is like generic. I think it's the same for all the packet. It's just literally inside the GRE header, there's the actual IPv4, IPv6 packet, something like that. But on top of that, it adds actual IP header with all the information. Change the information to the actual backend server. And also on the OSI layer 2, which is the data link layer, the MAC address will be changed to so this is a standard one. Like for every network hop, the Ethernet header will be changed with the MAC address. So in this case, the original Ethernet header will be from the client, its client MAC address, then to different like a router address. And from here, the Ethernet address will be from the Maglev as the source, and the backend MAC address would be the destination. So I would imagine we have the MAC address stored here as well, because that information is used to form the packet or update the incoming packet. Since the consistent hashing is an important step, I think we'll look into that later. But I think here we do all the process, we find out like which backend server to send to, we add the header. We have the example somewhere for the header, maybe not. But if anyone is interested, like we can go through that as well. I can provide exact examples. What is the IP header look like? What the GIE header look like? The new IP header and the Ethernet header. And so let's recap. What does the packet thread do? So packet thread as a packet thread, we do a VIP matching to see if it exists, it can be handled at the double check. If doesn't include it in the lookup table, this one, the VIP and lookup table matching, it will drop because, hey, I don't manage this. Simply drop that. And it will be handled by the client and also the server. So it won't be the load balancer's problem. And if it does, it will first check the connection tracking table. It's already there, already a record there. If not, we'll go through the consistent hashing and adding to the connection table. It find the backend information and then add it here. So next time we check this, it will reduce the step of checking this. And the merge active encapsulate the GRE, put it in the TSQ. So that's the outcome is. So the outcome of the packet thread processing, it is the packet. The packet is ready with the actual IP header and also with the GRE header in this packet. So the actual packet is updated without copying any data, and the pointer of that packet is added in the transmission queue. Now, next step, we have the maxing module, which is the module responsible for sending out the packet through the NIC. So this module periodically scans all the TSQs because there are many of them, each of them dedicated to a packet thread. And to scan all the TSQs, read all the pointers to see like they are ready to be sent out. So literally, I think it's just periodically read everything from the queue and put it in the ring queue for outgoing packet. So it's similar to the incoming packet ring queue. So in this ring queue, again, it's the same. All it stores is a reference to the actual packet, the location in the packet pool. And also it has had 3 pointers chasing each other to manage this queue efficiently and sufficiently. So when the pointers are first added, it's in the ready pointer is moving forward. And then if the packet is sent, collected and sent at the NIC, the pointer will be advanced as well. And then after the send, those places in the queue are in the recycled stage, so it can be reused for ready to accept other pointers to be added to the queue. So as you can see, again, the 3 pointers are chasing each other. So after mixing Maximoji placed the pointers in this queue, the NIC will read through this and see, hey, these are ready, and will read the pointer, find the actual packet, and send it out through the network interface to the actual backend, and then advance the pointer to mark this pointer reference to the packet pool as sent. So on and so forth. It will go in through very fast, maybe in nanoseconds, and then the queue can be reused for new items. So that's basically how the detailed works about how the packet is handled, adding extra layer, how to manage the incoming packets, the shared packet pool for efficiency, bypass kernel, no copy, and the outgoing queue is managed by Maxim module. And all this like super efficiency. I think it's a great design by Google. And here is some like relationships. The house checker in the forward module will check directly to the IP. IP, of course, it means the endpoint, in this case, the actual server. And each server will belong to one or multiple backend pool. And backend pool can have like different layers. Backend pool can contain another backend pool. And of course, each backend pool related to one virtual IP, and one virtual IP can be assigned to multiple backend pools. And all this managed through configuration file, the VIP and the backpool IP, the server endpoint IP. And just to highlight, the house checker will go directly to server endpoint. That makes sense because the pool cluster is just a logical grouping. You won't be able to check the house directly. And then another important concept in Maglev is the way it does consistent hashing. I think that will be the last topic I want to cover for Maglev. Again, it's a very big topic. If you have any questions, let's have like a direct discussion. I think that way makes more sense. So for Maglev consistent hashing, it involves like 2 stages. First stage, it generates a permutation for each backend server with randomly selected offset and skip value. So you can remember the 3 important concepts. It's a permutation, like an array, like for each backend server with a list of values. And with the start value, like the offset, and also the skip value, which the incremental value we add. And also another concept is lookup table size. So that the size of lookup table, not normally based on the white paper, it is a prime number. We can reduce the overlapping of values. I think all the details are listed in the white paper. You can read around that, but for simplicity, it works like this. For example, we have 4 backend servers. Let's say the table size is 11. In production, it's definitely thousands or tens of thousands or at that scale. We can imagine for B1, let's say the offset is 0, the skip value is 3. And so that means the permutation for B1 starts from 0, and next value in the permutation is 3. And then you need to mod the table size to make sure like still falls in the range. And so let's start calculating that. So start from 0, next one is 3, and then another plus 3, 6, 6 plus 3, 9, 9 plus 3, 12. Then we multiply with the table set, the remainder is 1, and we keep going. Add 3, 4, add 3, add 3, then 13, multiply 11, 2, 5, 8. Then you can see it populates the permutation for B1 with 11 values in it. And so it's kind of randomness, like from 0, 3, all the way to 5, 8. So that's basically if you want to like do some coding, this will be simply how it works. And then for B2, 3, 4, let's just assign this, just come up with them randomly. And as a result, we can see this other permutation table for each of the endpoint. So you can see this meets the first requirement. No, it's too soon. Okay, now that's the second stage. First stage is for calculation of permutation, and then next stage is to build up the lookup table. So how it works is, I think it's randomly select a starting point, maybe let's say starting backend server, maybe let's say B1 at this stage, maybe just directly in this order. And then we go round robin from like B1, B2, B3, B4, and then back to B1. So for B1, the first one it picked is 0. So at the 0 position, we fill in B1. And then for B2, its first choice is 1. Okay, fair enough. As B2, we fill in here. And then for B3, its first choice is position number 4. And I will put B3 here, and for B4, let's say B3, position 3 here. Okay, and then round robin, go back to B1. So B1's next preference is 3. It's already taken by like B4, and then it moves on to the next one, 6. So number 6, okay, yeah, it's still available. It will fill in as B1. And back to B2. So position number 3 already filled, and then yeah, position number 5 is available. So on and so forth. We go through each backend, and we go through their preference until we fill in the lookup table. And you can see it definitely the first benefit of consistent hashing is might the load is really evenly divided among the 4 servers. We have like 3 instances of B2, 2 instances of B4, 3 instances of B3, and 3 2 of B1. So as you can imagine, it's quite evenly loaded. 3 B1, 3 B2, 3 B3, 2 B4. And now we need to check if it meets the second requirement. It will have like minimum disruptions or redistribution after a node the server is added or removed. And so for saving the time, I have pre-calculated what would happen if we remove B2 from the backend server, backend pool. So as a result, this is like with B2 on the left-hand side, on the right-hand side is without B2. So you can see like only the only impact is like on the B2 side. It is replaced by like B3, B4, B1 very evenly. In this case, I think, yeah, for some reason it's a perfect match. In some other cases, of course, there'll be cases there are other changes. For example, B1, previous position is taken by B1, it will be taken by B3. There are possible cases. But you can see in general, like it will have the minimum impact on the lookup table. So let's solve some of the H1 approach of solving the problem about like not the load is not distributed evenly across the hash tree. I think in high level, I have covered everything about the Google Maglev white paper. So hopefully it helps you better understand about how it works. It might be difficult to read the paper for the first time. I totally understand that. But if you have any more questions on how Google Maglev works, you can leave a comment. We can have like I can reply to you, or we can have a brief conversation to go through all the details. If you can think about like, hey, how Maxi module works exactly, how do the pointers work exactly, how do they handle failure, and some of the like I said, it's quite a broad domain. A lot of scenario I haven't covered. Today we only go through at high level about how different things works. I didn't even cover this about like what exactly is announced and also what is the actual IP header is modified, etc. But hopefully it provide enough information for you to get comfortable or form a habit of reading the technical blogs or white papers. It will definitely beneficial for you as no matter you are preparing for an interview or just want to uh, improve your craft on software system design. All right, guys, I think it's a long topic, it's a long session. My voice is a bit hoarse at this moment already. Thank you for watching. If you want to have like a one-on-one coaching or if you have upcoming interview, you want to have a dry run with someone, please leave a message or book session directly with me directly. I'm happy to help and offer my support to get you the treatment where you want. Thank you, guys. See you next time.